Matter at the heart of a neutron star, the crushed remnant of a massive sun, is on the brink of becoming a black hole. For decades, scientists have wondered about the properties of that matter, the densest in the universe we can measure, and what form it takes. Now they have new insights thanks to NASA's NICER X-ray telescope on the International Space Station. A neutron star forms when a massive star's core runs out of fuel. With nothing left to fight gravity, the star collapses. Here, protons and electrons crush together to form neutrons, as well as lightweight particles called neutrinos that escape the star. The core continues to collapse until the matter at its center has twice the density of an atom's nucleus, but on a city-sized scale. When the core can't compress further, it rebounds. The expanding core crashes into the star's collapsing inner layers, creating a shockwave that rips outward through the star. The result is a powerful supernova explosion with a newborn neutron star at its center. Scientists have many questions about neutron star physics, including how squeezable is the matter in their cores? In more squeezable models, the internal pressure and density break neutrons in the center into a sea of even tinier particles, or combinations of those particles, resulting in a squishy core and a smaller star for a given mass. In some less squeezable models, the neutrons hold up against those forces, resulting in a larger star. Scientists used NICER's precise mass and size measurements of two pulsars, a kind of rapidly rotating neutron star, to narrow down how compressible these objects are. A pulsar is so dense that its strong gravity warps nearby space-time, allowing us to see light emitted from its far side. This distortion makes it look bigger than it actually is. The more massive the pulsar, the greater the warping and the larger it appears. Scientists measure this distortion by tracking the brightness of X-ray emitting hotspots on the pulsar's surface as it spins. They can then precisely determine the pulsar's mass and radius and obtain important clues about conditions in the core. NICER used this method to analyze J0740, the heaviest known pulsar with about 2.1 times the Sun's mass. Two research groups using different approaches both estimate it's about 16 miles across. NICER's measurements of J0740 and pulsar J0030 disfavor squeezable models, where cores contain only quarks or other exotic matter. And J0740's size and mass together challenge less squeezable theories, where cores contain only neutrons. Physicists will have to develop new models, perhaps containing both neutrons and quarks, to explain NICER's observations. The cores of neutron stars represent matter's final, stable form, short of becoming a black hole. Scientists can't recreate those conditions in Earth laboratories, so NICER will continue to measure pulsars to probe deeper and deeper into the hearts of these mysterious objects.